Hey, good evening, class. We are welcome to our class today. Today we'll be discussing the topic radioactivity. I remember when I asked my student one time what radioactivity is, they told me it's what happens in the radio. Well, radioactivity has nothing to do with that. So, let's dive in directly. Today we'll be looking at the history, types of radiation, half-life, dangers of radiation, uses of radiation, fission and fusion. It is nuclear fission and fusion. So, history. Um, Radioactivity or radioactive decay was first discovered by a French scientist called Henry Becquerel in the year 1896. He was working on phosphorescent substances, and then in his laboratory, he placed uranium, which is a radioactive element, on a black paper that had been on a film. Now, when he placed it, he noticed that there were spots on the paper that weren't there before he placed the uranium on it. So he figured out or he hypothesized that for this spot to have come on, that means this element had given off some rays or particles. And some years later, Mary and Marie Curie, they were Polish scientists. They started working on these elements, and then they actually did discover some elements. Um, Two major elements, polonium and radium. Polonium, which is named after the country they're from, that is Poland, and then radium because of the high radioactivity of the element. On your periodic table, you could check on this, you'll find them there. Now, they actually got awards. The Nobel Prize, they got Nobel Prize in 1903 and 1911. One of 1903 was in physics, and one of 1911 was in chemistry. But take note of something. Marie Curie died of aplastic anemia, which was said to have been possibly caused by excessive exposure to radioactive elements. She was always around with them. She had them in her lap coat pocket, had them on her table, she had them everywhere. And they even said back then our hands were kind of disfigured because of exposure to this. Which was until after her death in 1934 that they actually really got to discover the dangers of this radioactive element. We'll discuss more on this later. So, with this history at the background, let's move on to what radioactivity really is. Now, radioactivity or radioactive decay is the process in which unstable atomic nucleus loses energy by emitting particles or electromagnetic waves. Yeah. So, have unstable nucleus, and they on their own break down or emit this energy. Now, we could also define radioactivity as the spontaneous decay of a radioactive element. And when this happens, energy is given off. Now, when a nucleus of an isotope emits radiation, it is called a radioisotope or radioactive nucleus. So not all nucleus or not all isotopes are radioactive. We would see a few of these examples as we go on. So please let us take note of this. Radioactivity, just simply put, is a spontaneous decay of a radioactive element leading to emission of energy. Now, there are different types of radiation. Actually, there are three different types of radiation. We have the alpha decay or alpha particle, we have the beta decay or beta particle, and we have the gamma ray. We will see why gamma is actually ray and not particle. Now, alpha decay, yeah. So an alpha particle is made up of two protons and two neutrons. Now, when we add that up, that should give us 4. Now, when we talked about atomic number and mass number, there we figured out that elements that has two protons or two electrons and still has two protons and two neutrons, that should be helium. So because of this characteristic of the alpha decay or alpha particle. The scientists decided to use helium to represent this alpha decay or alpha particle. And well, that tells you that it is positively charged. Now, one thing about the alpha particle is that it has low penetrating power. When we say something has low penetrating power, it means it cannot go very far. Penetrating power is the energy required by an element to um should I say, go to a particular distance. Yeah. So it has low penetration power. It can be stopped by something as thin as paper. Yeah. And even the your skin can actually absorb this. So once it can be absorbed by something, that means that's where its penetration power stop. So it can be absorbed by paper, it can be absorbed by even the surface of your skin. So it has very low penetration power. However, it is in an electrostatic field, it is deflected to the negative side. Why? Obviously, because it is positively charged. Remember the normal rule? Like poles, unlike poles attract, yeah, and then like poles actually deflect. So now down there is an example of an alpha decay or alpha radiation. We see American a radioactive element having atomic number of 95 and atomic mass of 241. Now, when it undergoes this alpha decay, we see that it becomes, the element it produces now has an atomic number of 93 and an atomic mass of 237. Now, if you add 2 to 93, that will give you 95. And if you add 4 to 237, that will give you 241. So here, what happens is energy is given up, yes. There is a breakdown, yes. However, the alpha element or alpha particle is the one that takes the beat of this nucleus that has been broken down. So by the time you add the atomic mass and atomic number of the alpha particle, it should give you the same number as your original element. That is what tells you that it's an alpha decay or alpha radiation. So let's go to the second type, which is your beta particle or your beta decay. Now, what happens here is where we have high energy electrons that are released. Remember, electrons are negatively charged. So where high energy electrons are released, they are called beta particles. They actually have higher penetrating energy than the alpha particle. So they can pass through paper, yes, but they can be stored by thicker materials other than paper. Like aluminum foil, yes, that would prevent it from moving. So they are represented with the electron, and we know the electron has a negative charge -1, but it has a atomic number of 0. So the atomic number of the electron is 0, the mass number is -1. And now, obviously, because they have negative charge, they are deflected towards the positive side of an electrostatic plate. Now, we see an example here. We have the isotope of hydrogen, which is tritium, having the atomic number of 1 and the mass number or atomic mass of 3. We see that when it undergoes beta decay, it becomes helium having atomic number of 2, mass number of what? 3. Now, what happens there? You see that for it to have undergone this beta decay, it has added that is the -1. Remember that? Remember the -1 we talked about? So the -1 is there, and then 0 on the mass number. So that's what happens here. So this is an example of your beta decay. Now, we move to the gamma ray or gamma particle. Now, we said the others are we said the others are radioactive particles. So gamma ray, yes, occurs when particles collide. When particles collide, energy is released. Now, this energy can leave the nucleus in the form of wave or electromagnetic energy. So, unlike your rays, or sorry, unlike the particles that is that of alpha and beta, here we have the rays that come out like sunlight, something like that. But then, these rays cannot be seen with the naked eyes because they are electromagnetic. So for gamma radiation, it has no mass or charge. This type of radiation is able to penetrate most common substances, including metals. But something that blocks it is lead or concrete. And since it has no charge, it is not deflected in electrostatic plate. Now, a very beautiful and perfect example of your gamma ray, which is also a type of it, is your X-ray. Now, for those of us that have undergone X-ray, you would see that wherever it's being scanned, the light somehow passes through, and we see that they put something at the back to block, so it doesn't extend more than that. So it will pass through your skin, meaning your skin does not absorb it, pass through your bones, meaning your bones do not absorb it, and actually like go out. So the only thing that will block it is a wall. So gamma particles are that strong. So that means they have very high penetrating energy compared to the alpha and the beta. So now these are comparisons of the alpha, beta, and gamma. Yeah. So for alpha, we said 2 protons and 2 neutrons representing helium. For beta, we have the electron, and for gamma, we have the electromagnetic energy. Change in elements here for alpha, yes. We remember for each have undergone alpha decay, that means helium or an element using helium has to have been added to it. For each have undergone beta, yes, an electron, but for gamma, no, it's 0, 0. Now, for penetrating energy, we see that for alpha is low, for beta is on the middle side, and for gamma is very high. Now, this shows how the type of radiation actually move and what blocks them. We see alpha there, blocked or absorbed by paper. We see the beta blocked by aluminium, but we see the gamma ray passes through paper, passes through aluminium, but is blocked by lead block, or some other cases, your concrete, something very hard has to actually block it for it not to move on. So these are types of radiation. Now, let's talk about something we call half. We'll still come back to this and we'll see some other examples on the alpha, beta, and gamma. So let's talk about half-life. Now, what is half-life? Half-life is the time it takes for half the atoms of a radioisotope to decay into other elements or other atoms. So what do we mean by this? Say you have example, let's pick one of these here. Say you have sodium 24. For those of you that really studied the periodic table, would know that sodium, the normal sodium, has atomic mass of 23. But this radioactive sodium here has atomic mass of 24. Now, the half-life of this is 15 hours. And what does that mean? That means for every 15 hours, this sodium 24 will divide to half its normal size. So let us say you have 8 grams of sodium 24 in, say, a human, because we do have some of these in our system. We have radioactive potassium, we have also carbon and the others like that. Yeah, so let's say this sodium is in the body and we have 8 grams of it. Now, that will mean that at this point, it's 0 hour. In the next 15 hours, that 8 grams should have divided to half its size. That will be 4 grams. Adding 15 hours, that will be 30 hours. To have divided to, that 4 would have divided to half. That will be 2. And adding another 15 hours, the 2 would have divided to half. That will be 1. So Half-life is the time it takes for a radioactive element to divide to. I'll see carbon-14 here. This is a big one. It takes about 5,760 years. So for it to divide to half its size, that would be like about 11,000 years or thereabouts. So for 11,000 years, this carbon is that's in 8 grams. For 11,000 years, divide to half of its size, that will be about 4 grams. So we get, I hope we get it now. So you might, in your external exam, might be told to estimate the half-life of the substance. Now, all you have to do is just check, okay, what is the percentage of that substance? Say it's 100% at 0. Okay, let's say it has half-life of 20, and then you calculate its half-life in 200 years. So you have to go like for it to be able to get it to that 200 years. And that's for half-life. So you see different elements here. So half-life can range from a few seconds, as in polonium, see 0.16 seconds, to uranium, billions of years, here about 7.1 billion years. I do not know of your life to actually see half-life with this. So that's half-life. Now, the dangers of radiation. What are the dangers of radiation? Now, oh, sorry, I didn't hear that thing. Damage to cells. That's what's supposed to be damage to cells. Now, what happens when the person is exposed to radiation, a high amount of it? The cells actually react to it, can lead to destruction of the cells. The cells can die. Remember, these cells are actually quite fragile. So when they're exposed to radiation, the cells can actually. This leads to something else. While some do not die, some could actually react in another way and undergo what is called mutation. I'm sure we've heard about that in our biology. So that's where the other part comes in, genetic abnormalities. Now, this is where they have been exposed to radiation. Say, for example, Hiroshima, where we had the atomic bomb. I do know that now they are still have been affected by this radiation due to their genes have been affected by this. Now, aside from mutation that could occur in plants, animals, and humans, which could actually be a gradual process, we still have cancer. Now, it has been said that some cancers, or most cancers, are linked to radiation. Radiation coming from our phones, radiation coming from devices around, there are questions about it. And well, we'll see how this deal comes about. Some of this as a result of the usage. Now, let's now talk about the uses of radiation, about chemistry and genetics. Today, um, radioactivity is used in biochemistry to study the genes to get to understand transformation, exchange of some of the codings and rest like that, adjustment and testing and things like that, which are being used today to make different types of plants that grow in quick time, chickens and other things like that. Being speculated here though, but um, gene replacement is one thing that has been carried out. Now, also in our environment, radiation is being used either small scale or large scale for sterilization and other things like that. Your UV light is also a form of radiation, and you do know that. So this is being used for sterilization. Even in water treatment, we have UV light that is being used. So archaeology and carbon dating. This is also known as fossil dating or checking of fossil records. where we hear that they discover bones of um, dinosaurs and things like that. Well, we do hear sometimes where they give age of these bones. Well, you cannot just look at a bone and just say, oh, it's 700 million years old and things like that. So it's actually through carbon dating that they are able to check, okay, what is the age of this bone? Remember, based on our chart here, say carbon has half-life of 5,760 years, and every human, every plant has a definite or an amount of carbon in them. We as humans, we exhale carbon. Yeah, we exhale carbon dioxide, yes, but that means it is still in us because we feed on plants carbohydrates, and in fact, everything we feed on has a measure of carbon in it. The plants themselves, they take in the oxygen, and the food they produce has carbon, still has carbon in it. So the point is, every living thing on this earth has carbon in them. So carbon dating is where, okay, we see the fossil, we check how much of the carbon is still remaining. It's based on, yes, most take about 5,000 years for it to disintegrate. So how much of it is remaining? By the time you check the half-life of the amount of carbon that's still remaining in it, it will give an approximate amount of years that that animal had been dead and possibly been in existence. So let's say they check and they say, oh, it's just about 50% remaining. So that tells you that that animal has been dead for about 11,000 years. Oh, let's so now yeah, we talked about the uses of radiation. Now let's talk about nuclear fusion and fission. Nuclear fusion is a process of reacting two atoms to form a heavier nuclei. So we have two atoms reacting them together to get a heavier nuclei. Naturally, we have this in the sun. If you've read about the sun or watched documentary about the sun, say it is just gases actually burning. Now these gases or nucleus are coming together and they are being forced to react. Naturally, they should not react, but forcing them to react causes that release of energy. So it's that release of energy that we see as the light and the heat that we're experiencing from the sun. So what happens in the sun is actually nuclear fusion. These gases bombarding each other and releasing energy. And well, it is this same thing that is used in producing hydrogen bomb, forcefully reacting two hydrogen atoms together, making them to combine by force, causes a release of energy and heat, leading to explosion. That is nuclear fusion. Now, for nuclear fission, this is the process where the nucleus of an atom splits into two or more smaller nuclei. Now, this would not happen naturally on its own in some cases, except from your normal decay. But when it is forced, they have nuclear fission. So we have an element that is already stable and we now force it to break. Forcing it to break leads to release of energy. It's an endothermic reaction. So heat is released, energy is released. Example of this is your atomic bomb. So when you try to force it apart, actually leads to explosion. Yeah, and what we've noticed is forcing them together actually causes more damage than trying to split up one. So there's more energy release when you're trying to break apart, when you're trying, so when you're trying to force them together, and when you're trying to break them apart. So I said we'll come back to some of the examples of this alpha, beta, and gamma. So I want to give some examples. So let's take uranium now. Uranium 235. Um, Let me use here for it. Now, say you have uranium. So, 5. And say it has atomic number of atomic number of 92. Now, if this is to undergo your alpha decay, what you have is an element, thorium, having atomic mass of 2, 3, 1, and atomic number of 90. Why? Because it would have produced helium as having atomic number of 2 and mass number of 4. I hope we get it. So here we have alpha decay, uranium 235 with a mass number of 90, atomic number of 92. So it is to undergo an alpha decay. The product should be, by the time you add the atomic number of helium to the atomic number of the new element, it should take you back to the same atomic number as uranium. And by the time you add the atomic mass of helium and the atomic mass of whatever you are getting, it should take you back to the atomic mass of uranium. That's how it works for that. Now, for the case whereby you have say your beta decay, for beta decay, let's say you have hydrogen 3, 1, say this is tritium. Now, by the time this undergoes your beta decay, what you should have should be helium here, 2, 3, plus electron minus 1 and 0. Now, 2 plus minus 1, that should give us 1. 3 plus 0 should give us 3. So I hope we get it. This is for beta decay. This is what it usually looks like. For beta decay, what you just do is you add 1 to the atomic number of the element that is produced and 0 to the atomic mass. That will give you your beta decay. Now, for gamma, if you say an element undergoes gamma, actually, I didn't mention it. That one is represented using M00 neutral. So, say it is helium itself. Let's just give an example. No, helium is not it now. But let's just say it is helium 4, 2. If it has undergone it, it will still remain as helium 4, 2 plus n 0, 0. So there is no change at all, as we saw in that table. There's no change when it undergoes gamma radiation. So please, let's just take note of it. It's quite simple. It's not complicated. You just have to know how to add up the elements representing it as helium, electron, and neutral element 0, 0. Now, this is example of your fission, sorry. We have radioactive elements here, uranium 235. Now, neutron bombards it. Now, what happens? It becomes uranium 236. That is, that's added 1 to its atomic mass. Now, because of that, it needs to release all that, all the neutrons all the neutrons that are now in it, with massive release of energy. Now, it is this massive release of energy that leads to the explosion because it has undergone the first reaction. So that's about that. So, um, by way of recap, the radioactivity was discovered by Henry Becquerel in the year 1896, and then later on, some other people worked on it, Mary and her husband, Mary Curie, and in 1903 they got Nobel Prize in Physics, and in 1911 they got another chemistry. Well, their work was useful later on. You see, in 1914 during the World War One, whereby the X-ray reading came into place. Yeah. And then we say radioactivity or radioactive decay is the process whereby unstable atomic substances emit particles spontaneously, most times on their own. We said, a substance that undergoes this is called a radioactive isotope or a reactive nucleus. So there are three types of radiation: alpha, beta, and gamma. Alpha particles are positively charged, have low penetrating energy, and then they also reflected to negative pole on the electrostatic field. The beta are negatively charged, have a higher penetrating energy, and are deflected to the positive side of pole. They are actually stronger than helium. Now, for the gamma rays particles, these are not deflected. They have no charge, and they have the strongest penetrating energy and stop time. Things as strong as lead, and even your your concrete can also stop it, or it can also absorb it. Now, this table shows the comparisons of these three: the alpha, the beta, and the gamma. Here we see how the alpha is being absorbed by paper, the beta by aluminum, and the gamma by lead block. These are things that can stop them from moving. Now, we talked about half-life. Sometimes it takes for a substance to get to half of its original size. Here we say we have something 100% at its half-life should reduce to 50%, at another half-life to 5%, and that's how it continues to diminish till it goes into non-existence. And the half-life varies from seconds to billions of years, depending on the element that is involved. So what are the dangers? Excuse me. So talk about dangers: damage to cell, genetic abnormalities, cancer, the use of radiation, the chemistry and genetics, the environment, sterilization of water, even sterilization of clippers, and barbing salon and the others. Yeah. And then archaeology and carbon dating, checking the age of the substance, or sorry, the fossil has been dead for a very long time. Yes. Then nuclear fusion and fission. Nuclear fusion is coming together. Nuclear fission is splitting up. Let's just keep it that simple. Fusion coming together, fission splitting up. Example of fusion: the sun, hydrogen bomb. Example of fission, atomic bomb. So this, as says, an example of fusion. So this is what we have for today. I don't know if anyone has a question to ask based on this topic. Is there any question? Okay, there's no question. Take it as that. Or,
Excuse me, sir.
yes.
Please, the dangers of the damage of is it damage or danger? Okay, the danger of radiation, the cancer side. I do not really understand the cancer.
Okay, yes. Now for the cancer, we are exposed to radioactivity. Our phones, microwave, even for those of us that live close to this satellite mass, we are being exposed to radiation. So what happens is by the time you're exposed to a high amount of this, it starts reacting with your cells. And as it starts to react with your cells, what happens is the cells begin to become abnormal. It now becomes like a cell now becomes like a lump. Let me just put it that way as an example. It becomes something like a lump, and as that cell now continues to reproduce, and while there are cells that are supposed to fight it off, it becomes so strong that these other cells cannot fight it off. So it begins to reproduce, reproduce, and reproduce. And that is how the cancer actually comes up, depending on where it is found. Um, Another big way, yeah, I didn't mention it. For people that undergo X-ray, remember we said X-ray itself is a type of radiation, gamma ray specifically.